Welcome to today's lecture on exponents and roots. I'm Drew Collop. In a previous lecture, we briefly touched on what exponents are. In today's lecture, we will go into more detail and include roots as exponents. When working in science, oftentimes you're working with either very large or very small numbers. For instance, the number 6.0220000 000000000000000. That's a very large number. It would be much easier if we could write that in a different format. We do. We write that as 6.022 times 10 to the exponent 23. This is known as 1 mole of something. We'll talk about this in more detail, and you'll learn about this all in your chemistry class. In the next lecture, we'll be talking about scientific notation. Before we get there, I want to make sure you understand how to work with exponents. It doesn't just work with very large numbers, it also works with very small numbers. This number right here, it's not practical to write that number down or even use it in our calculator as such. So therefore, we could write that number as 6.022 times 10 to the minus 21. Again, we have exponents there. So scientific notation is how we're going to work in science with very big and very small numbers. Therefore, you must fully understand how exponents work. We reviewed this earlier. This is your base, and this is your exponent. The base is a standard size of font, and the exponent is a superscript size font. And again, 2 to the 4 is 2 times 2 times 2 times 2. It's 2 multiplied by itself 4 times. This would be 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. We covered the exponent laws earlier. Let's review them again. When we're multiplying exponents with the same base, what we can do, so we're multiplying these together, that's what the dot means. What we can do is we can combine them as a single exponent. And what we do, we add those two exponents together because we're multiplying them. 2 to the 5. We already covered this in a previous lecture. Just to make sure you understand, give these practice problems a try. The first two are pretty easy. Let's take up the last 4. So here we have the same base of 10, so we can combine that as a single exponent. We're multiplying, so we add them up. You don't see an exponent here, but there is one. It's 1. So this becomes 2 plus 3 plus 1, giving me 10 to the 6. Here we have 6 to the exponent negative 2 times 6 to the exponent 3. Again, we have the same base. We're multiplying them. I can combine them together. That's minus 2 plus 3 gives me 6 to the 1. Down here, same base, we're multiplying it. We combine them. Minus 4 plus minus 2. This gives me 8 to the minus 6. And lastly here, we have 7 to the exponent 5 times 7 to the exponent minus 8. Combine them as a single fraction. We add them together. 5 plus minus 8. This gives me 7 to the minus 3. Let's review the exponent law when we're dividing two exponents with the same base. So as long as they have the same base, here or here means the same thing. What we do is we combine them and we subtract them. The exponent that comes after the division symbol, that's the one we subtract. Give these a try on your own. Take them up. 4 to the minus 1 divided by 4 to the positive 5. So here, same bases, combine them, minus 1 minus 5, 4 to the minus 6. Here we have 5 to the 4 divided by 5 to the 8, 5, 4 minus 8, 5 to the minus 4. The next one is tricky. Here we have the same base. We can combine them. 3 minus minus 1. Minus and a minus is a positive. 3 plus 1 equals 6 to the 4. Be careful of that. What about the next one? Can't do it. Exponent laws don't work on it. We'd have to expand it. We could do that. Our exponent laws do not apply. Why? Different bases. Lastly here, both 7s, 7, 5, minus 7. Again, two negatives make a positive. 7, 5 plus 7, 7 to the 12. So be careful when you have a negative exponent and you're dividing it. Try these now. We're going to combine multiplying and dividing of exponents. Give these a try now. Let's take them up. You can see we have a base of 2 in all of these. Let's do them one at a time though. Let's combine those two first. 2 to the 10 divided by 2 to the 9. Now we can combine those two. 2 to the 1. Or simply just as 2. Next up, we have all 6s. Let's combine these first of all. This is 6 to the 1 times 6 to the 5, giving me 6 to the 6. Over here, you can see we have minus 2 now. The minus is part of that base. Minus 2 is the base. Let's combine these together. Minus 9 divided by minus 2 to the negative 1. And here we get minus 2. We're subtracting minus 1, which means we're adding 1. This is 2 to the minus 8. Down here, all 4s. Here, I'm dividing two exponents with the same base. So I subtract them. This is 4. 6 minus minus 2, which means 6 plus 2. 4 to the 8. 4 to the 2. Add those together. 4 to the 10. What about here? We have 2 of the same bases. You don't see an exponent there. We assume it's 1, so we add them up. This is 5 to the 5 divided by 2 squared. Exponent laws now? Nope, can't do it. Different bases. We'd have to expand it out, but different bases, so our laws don't apply here. We can still solve it. You just do 5 to the exponent 5 divided by 4. Again, we have minus 5 as our base. We have an exponent of minus 6. We're dividing it, so minus 6 minus minus 2, so we're adding 2. Minus 6 minus minus 2, so we're going to do an extra step here. And then we have minus 5. Minus minus makes a positive. We combine those together. We're adding them now. Minus 4 plus 4 is minus 5 to the 0. And what happens when we raise anything to the exponent 0? It's equal to 1. So make sure you understand these exponent laws. We're going to use them quite a bit in this course. Here's another exponent law we learned about, and oftentimes this is the one students mess up on. This is when we have an exponent and we raise that exponent to another exponent. Oftentimes what happens, students, they confuse this with the multiplication one, and they say this is going to be 5, 3 plus 2. Wrong. Don't do it that way. We multiply them together. This is 5, 3 times 2, which gives me 5 to the 6. If you don't believe me, expand it outwards. 5 cubed times 5 cubed. That's what that means. We're multiplying two values to the same base, so we add them up. 5 to the 6. Give A through D a try right now. Let's take them up. Here we have 3 times 4. This is 3 to the 12. Here we have an exponent raised to the exponent. This is going to be 9 minus 2 times 4. 9 to the minus 8. Here we have 8 minus 1 times minus 5. Two negatives make a positive. 8 to the positive 5. Here we have a base of 2 to the minus 3. We raise that to the minus 2. Notice the negative sign is outside the brackets. This means those exponents do not apply to the negative sign. Can keep that outside the brackets. 2 minus 3 times minus 2. Minus 2. Here we have minus 3 times minus 2 is positive 6. We can drop those brackets. Minus 2 to the 6. Now notice here, this 6 only applies to the 2. If I wanted it to apply to the negative sign, I would have to write it like this. Those two things do not mean the same thing. This will be a positive number. This will be a negative number. Because here, it doesn't matter what we get, it's going to be negative in the end. Here, it's an even number of negative signs, therefore it will be positive. So if you want to include the negative with the base, make sure you put brackets around it. E through G are a bit more challenging. I'd like you to try these on your own, and then we'll take them up. Let's take them up. Here we have an exponent raised to exponent. We multiply them together. Minus 1 times 3 is minus 3. On the bottom here, 2 to the positive 6. And that's as far as we can take it right now with exponent laws because they have different bases. You could take it further. You just have to expand your exponents and then work with those numbers. Let's try f. 0 times minus 4 is 0. 2 times minus 2, minus 4. Anything raised to the exponent 0 is 1. Remember what I can do? I can take a negative exponent, turn it into a positive exponent by bringing it up to the top. This is 10 to the positive 4 over 1, which can be just 10 to the 4. Here we have 7 raised to the exponent minus 3 and then raise that to the exponent 0. We're going to multiply those together, giving us 0 on the top. On the bottom here, we have 10. Minus 1 times minus 2 is positive 2, giving me 1 over 10 squared. Quite often, I'll ask you to leave your exponent as a positive number. So in this case here, positive. In this case here, positive. This should have been review. We covered this in a previous lecture. Now, I have spoken about this in previous lectures, but I haven't actually specifically taught it. This is when we have a product raised to an exponent. If we have the product means multiply. If we have the product of two values raised to an exponent, I can just distribute those terms there. This gives me x squared, y squared. X times y, this is a single term. Terms are separated by addition and subtraction signs, therefore this is one single term. Please note, this rule does not apply when we have two separate terms. So here, x and y are separated by a positive symbol. Therefore, these are two terms. We cannot do that. Why not? Well, let's expand that outwards. X plus y squared is this. We distribute here and here, here and here, and you can clearly see this and this are not the same thing. So only when you have a single term can you distribute. Let's do a and b together. Here I have 2x in brackets raised to the exponent 2. Notice the brackets around the 2 and the x. That means the exponent applies to everything. It is one big term because it's all multiplied together. Therefore, I can do this. This gives me 2 squared, x squared, 4x squared. Over here, same thing. 10 times x squared times y cubed. Raise that to the exponent 5. The brackets are around there, therefore this is one big term, and I distribute the 5 to all terms inside. 10 to the 5, 2 times 5 is 10, 3 times 5 is 15. And I can expand that outwards. 1, 2, 3, 4, 5. Final answer. Same rules apply when we have a quotient raised to an exponent. If it's one term, we can distribute it between all the variables or the numbers inside. X cubed over y cubed. Let's try these together. So here, one single term. I can distribute here, 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 and here to every value inside. 2 squared, x squared, 3 squared, y squared. Notice it has to go on every number and every variable. This gives me 4x squared over 9y squared. Let's try b now. Again, it goes to all the variables in the numbers because it's one single term. 5 cubed, x cubed, y cubed over 3 cubed, z cubed. 125 x cubed, y cubed over 27 z cubed. Once again, we can do that because both of these are single terms. The numbers and variables inside are separated by multiplication symbols and division symbols only. They are not separated by addition or subtraction symbols. We spoke about negative exponents. Let's review those as well. So I can make any exponent into a positive exponent by moving it to the opposite side of a fraction. Here's 2 to the minus 7. Let's turn that into a fraction. I can take that base and bring it down to the bottom. This gives me 1 over 2 to the positive 7. Quite simply like that. That also works the other way. If I have 1 over x to the minus 3, I can bring the base of x up to the top, and this becomes x to the positive 3 over 1, which is just x to the 3. I want to point out something for you. We have 2x to the minus 3, and I have 2x to the minus 3. Please note, the brackets are important. In this situation here, the minus 3 is only applied to the x. In this situation here, the minus 3 is applied to both the 2 and the x. If I said, make all your exponents positive, in this case here, what goes down to the bottom? Just the x. If I wanted to turn this one into a positive exponent, what goes down to the bottom? Both the 2 and the x. Because of the brackets, it makes the minus 3 apply to both the 2 and the x. So be aware of that. On my test, quite often, I'm going to ask you for simplified answers given as positive exponents to make you understand how to move the exponents up or down. Quite often in the lab, you'll see something like this, grams per mole, represented as grams times moles to the minus 1. You can see these two things mean the same thing. In one case, it's grams over moles. In the other case, we move the moles up to the top. And this is going to be grams times moles to the minus 1. So if you see something like this, all it means is that that is in the denominator. Let's give some of these a try. So I'm going to answer these, and I want the final answer to have a positive exponent. So here I have two of the same bases. I'm multiplying them. Therefore, I can add these together. 5 to the minus 2, giving me 1 over 5 squared. And if I wanted to, I could expand it even further, 1 over 25. Example 8 here. Well, I want to make the 2 to the minus 1 a positive exponent. I bring that down to the bottom. Notice here I have 3 to the minus 1. I want to make that a positive exponent that comes up to the top. This gives me 3 to the positive 1 over 2 to the positive 1, which gives me 3 over 2. Also note, remember before we could distribute an exponent out. We can also remove an exponent. We have the same exponent of minus 1 on the top and bottom here. What I can do is I can take that exponent out because it's the same. This gives me 2 over 3 to the minus 1. So please be aware, those mean the same thing. Here's some practice problems, A, B, C, D, and E. Please give them a try and we'll take them up. So here, we can distribute this value both here and here. This gives us 1 to the minus 1, 3 to the minus 1. I can bring this down to the bottom and this up to the top to switch the signs. 3 to the positive 1 over 1 to the positive 1, which gives me 3 over 1, which gives me 3. Alternatively, if you see that your exponent is minus 1, we can just take that fraction and immediately flip it. Make it positive 1. One of those little tricks. Let's try B. Minus 2, 1 to the minus 2 over 10 to the minus 2, giving me, in this case here, 10 to the 2 over 1 to the 2. In this case here, 10 to the 2. 1 squared is just 1. 10 squared, which gives me 100. Again, alternatively, we see there's a minus sign. I can flip this, make that a positive symbol. 10 squared equals 100. Now we have minus 7 over 8, raise the exponent 0. Let's distribute that here and here if you wanted to. Minus 7 over 0 over 8 to the 0 gives me 1 over 1, which is equal to 1. But anything raised to the exponent 0 is 1, so we could have just skipped right from there to there. D and E now. Let's distribute. Notice the brackets are around the 2 and the minus sign. We will flip it to bring this up to the top to make it positive and bring this down to the bottom to make that positive. 3 to the 3, minus 2 to the 3. 3 cubed is 27. Minus 2 times minus 2 is positive 4, times minus 2 is minus 8. This gives me minus 27 over 8. Last one here, let's use that little trick where if we have the whole thing is negative, I can flip it and change that to a positive value. Now I can distribute both here and here. Notice the minus sign is in brackets with the 4. Minus 4 times minus 4 is positive 16 over 9. We can convert that to a mixed number, 1 and 7 over 9. Let's now turn our attention to something new we haven't taught in this course, fractional exponents. This is when we have an exponent as the fraction. Now the numerator and the denominator of this means two different things. First of all, the numerator represents the exponent. You can see right here. The denominator represents the root right here. So that is how roots come about. They are fractional exponents. Let's now examine what this represents. What we can do first is we can square the 4. 4 times 4 is 16. Then we take the cube root of that. The cube root of 16 is 2.519841. And we would maybe round that off with significant digits. For now, we're just going to explore how to use this in our calculator. So we can use the cube root button. Alternatively, you could type in 4 to the exponent, put in brackets, 2 divided by 3, and you should get exactly the same value. So you can either use fractional exponents or you can use your root buttons and your exponent buttons to solve these problems. I'd like to point out one additional topic here. Let's say we had the cube root of 8. The cube root of 8, we're looking for 3 of the exact same numbers that multiply together to give me 8. Well, that's going to be 2 times 2 times 2. So the answer to this is 2. What I want to show you is why it becomes 2. Let's turn this expression into a fractional exponent. However, first I want to convert 8 over to what it would be in terms of base 2. 8 is going to be 2 times 2 times 2. It's 2 cubed. And then we're taking the cube root of that. Let's now convert this to a fractional exponent. So we have our numerator is 3, our denominator is 3. Notice what that is. That's 2 to the exponent 1. And that's why it disappears and we get 2. Again, our exponent is the numerator or top number, and our root is the denominator or the bottom number. And they cancel each other out here, giving me 1. Now, after all this, you might say, why are we doing any of this? I could just use my root button. Well, let me explain something for you. Later on in calculus, you're going to get a problem like this. 2x plus 3, you have to take the square root of the whole thing. Then it's going to ask you to take the derivative of that. You are going to want to know how to do this properly. Y is equal to 2x plus 3, put it in brackets, and put that to the exponent 1/2. Those things mean the same thing. So, for calculus in Math 273, try and remember this. Let's explore a couple of these. You can see there's a little pocket there in the root symbol. If there's nothing there, we assume it is a 2. So this can be expressed as square root of 4, or 4 to the exponent 1/2. We have cube root, fourth root, and fifth root. And these again can all be expressed as fractional exponents. Let's try 10 together. Simplify. So I have 4 to the exponent 3 over 2. What does that mean? Well, here, this value here is our exponent, and this value here is our root. So we're going to have 4 cubed, and we're going to take the square root of that. 4 cubed is going to be 4 times 4 is 16, times 4 is 64. Then I take the square root of 64. What two numbers multiply together to give me 64? The answer is 8. In this case, you can see the exponent was inside the root symbol. It doesn't matter whether it's inside or outside. For instance, I could have written it as such. Still the square root, still cubed. Let's take the square root of 4, which is 2, then we cube it, that's equal to 8. So you can see it doesn't matter whether the exponent is inside the root or outside the root. Try the next one on your own. Let's take it up. So again, we have our exponent is the top number, our root is the bottom number. So this is the cube root of 27 to the exponent 4. We could also write that as the cube root of 27 to the exponent 4. It means the same thing. The upper one's actually easier to solve than the lower one. The cube root of 27, 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27. So that's going to be 3 to the exponent 4. 3 times 3 is 9. 9 times 3 is 27. 3 times 27 is 81. If we do it the other way, now we have to work out 27 to the exponent 4. In which case you need a calculator. And then you take the cube root of that with a calculator, and we get 81. Even though we can place the exponent either inside or outside the root symbol, it's often easier to do it one way versus another way. Let's cover the last part here, roots and radicals. This symbol here is actually called the radical symbol. That's its proper name. If you're doing algebra and you have to take the square root of a number using algebra, oftentimes there's going to be two answers, as such here. You can see right here, x squared is equal to 16. So x squared is equal to 16. In algebra, how we get rid of the squared now is we take the square root. And we do the same thing to both sides. Remember what this is equal to. We can turn this into a fractional exponent. X, here our exponent is 2, and our root becomes 2. And this is the square root of 16. What is this equal to? It's equal to 1. X to the 1 is equal to square root 16. So x is equal to, what's the square root of 16? Square root of 16 is 4. I'm looking for two numbers that multiply together, two of the exact same numbers that multiply together to give me 16. So the answer is 4. But not quite. There's two correct answers. The answer is both positive 4 and negative 4. Positive 4 times positive 4 is positive 16. Negative 4 times negative 4 is positive 16. 4 times 4 is 16. Negative 4 times negative 4 is positive 16. Please note, if you're doing algebra, there's going to be two answers. However, if you're just asked to solve this and you're not doing algebra, this is called the principal square root, and it's always positive. Square root. In this case, it's always positive. If you're just dealing with radical signs and square roots on their own, there's only going to be one answer. It's always positive. However, if in the course of algebra, when you're solving for x, you have to take the square root of a number, the answer is both positive and negative. Let's look at this problem now. X cubed equals 27. Again, we want to do the opposite. I'm cubing it, so I'm going to take the cube root of both sides. In doing so, you can see this gives me x. 3 over 3 is equal to the cube root of 27. 3 over 3 is equal to 1. Cube root. I would need three numbers that multiply together, three of the exact same numbers that multiply together to give me 27. It's going to be 3 times 3 times 3, so the answer here is 3. X is equal to 3. Plus or minus? Only plus 3. 3 times 3 is 9. 9 times 3 is 27. Minus 3 times minus 3 is positive 9. Positive 9 times minus 3 is negative 27. So when you're doing algebra, if you have an even root, there's going to be two answers, potentially. If you have an odd root, there will only be one answer. Let's work with this one right now. 36 to the exponent 1/2. That's going to be square root of 36. What's the answer to that? The answer to that is 6. Only positive 6. Why? Because we're not doing algebra here. We're just solving an expression. Again, the positive and negative only come out when we're solving for algebraic equations. What about here? Convert that over. We have 32. We have 2 over 5. What is the fifth root of 32? It's going to be 2. 2 squared is 4. Again, we're not doing algebra here, so there's only one answer. But in addition, this is an odd root. So even if we were doing algebra, there would still be only one answer. Here's a number of roots. It could be helpful to work out these. Let's solve them right now. Square root of 1 is 1, 2, 3, 4, and 5. You can use your calculator for all these, but if you can do these quicker in your head, it's much better. So if you're just solving for radicals, there's only one answer, it's positive. If you're solving an algebraic equation, there's going to be both positive and negative answers. For cube, 1, 2, 3, 4, and 5. This is a cube root, so it doesn't matter whether you're doing algebra or you're solving for the principal square root, it's always going to be positive. And for your fourth root, again, it's going to be 1, 2, 3, 4, and 5. Committing some of these to memory will help things along. If we had the cube root of minus 27, can we solve that? I need three numbers that multiply together to give me minus 27. So minus 3 times minus 3 times minus 3, does that work? Minus 3 times minus 3 is positive 9. Positive 9 times minus 3 is minus 27. The answer here is minus 3. So when you're dealing with odd roots, 3, 5, 7, so on and so forth, you can have a negative value under the radical sign. However, when we're dealing with even roots, for instance, I want you to solve the square root of minus 16. Try that now. Try your calculator even if you like. You should have seen you get an error with your calculator. Let's see why. Well, two numbers that multiply to 16. 4 times 4 is 16. What about minus 4? Minus 4 times minus 4 is positive 16. There don't exist two of the same numbers that multiply together to give you a negative value. Let me write that down. There is no way to multiply two numbers that are the same to get a negative number. Can't do it. Two positives are positive, two negatives are positive. How do we get around this? Because sometimes you have to do that. We talked about this on day one. We talked about there are real numbers. There are also imaginary numbers. And usually we call the square root of negative 1, we call that I if you're interested. So we can solve this. This minus 16 square root, we call this 16I square root. This is just to tell you that something exists. We will not be using imaginary numbers at all in this course. So during this lecture, we reviewed a lot of what we already covered in terms of exponents. We talked about fractional exponents, and we talked about roots and radicals. At this point in the course, we have now completed the foundational mathematics necessary to do well in this course. We do this to make sure everyone is on the same footing moving forward. With the next lecture, the content will start getting more difficult, and we'll start relating it more to the lab as we move along. Until next time.